we need to talk about it, and we have one of the authors of DD-log here, so I'm hoping that we can spend some time tonight or tomorrow talking over the different options. Yeah. All right. So the next talk in our session here is titled "Extending OVS Packet Processing Pipeline at Runtime Using P4," and here is Tomasz from Orange Labs. Yeah.
Okay, so hi, my name is Tomasz Osiński. I'm from Orange Labs at Poland. I'm also a PhD student at Warsaw University of Technology. And today I'm going to present you our last year effort around extending vSwitch packet processing pipeline at runtime using P4. In particular, I'm going to tell you about our two contributions. A first contribution is a design and implementation of programmable actions as BPF programs inside vSwitch. And this contribution allows users to inject and data plane programs, arbitrary data plane programs, to the packet processing pipeline of vSwitch at runtime. And it is partially based on the vSwitch, which has been presented last year by Paul Chagnon. Second contribution is P4-uBPF compiler, which is a new backend for the P4 compiler. And it allows users to write data plane programs, data plane extensions for vSwitch in the P4 language and inject them as vSwitch actions at runtime. Before we go to the design and implementation, I would like to quickly say about our motivation. So as you may already know, P4 is a high-level programming language to describe a data plane of networking devices. And it has three main features: the expressiveness of the language, protocol independence, and also target independence. And these features are especially interesting for service providers, as they can take advantage of the expressiveness of the language and implement a data plane of the virtual network functions on their own, and further offload data plane functions to the high-performance platforms running inside the telco cloud. And the first step to implement this concept is to use virtual switches to offload the data plane to the virtual switches, such as vSwitch. However, in order to do that, we need to have a runtime programmability provided by, for example, vSwitch. So we need to be able to inject programs at runtime without recompilation. And it was our goal to build such a solution for the VNF offloading use cases. So we started from analyzing different solutions. There is a PISCES work which implements a really first implementation of P4 capable vSwitch. However, it requires recompilation every time the P4 program is changed, so it was not the case for our use cases. There is also a soft flow solution which does not support P4 but allows to inject arbitrary programs, network functions in the pipeline of vSwitch. And finally, there is vSwitch, which provides the support for stateful packet filters by integrating a user space BPF virtual machine with the data path of vSwitch. And it does not also support P4, but it provides the runtime extensibility mechanism in terms of BPF virtual machine. So it was a good starting point for us, and we based significantly on this solution. As I said, OCO provides the support for stateful packet filters by integrating a user space via virtual machine with a user space data path of vSwitch. And the PPF programs that are injected to the virtual machine act as additional match fields from the perspective of vSwitch. And it's integrated with a flow caching architecture. OCO also provides the BPF verifier, which ensures the correctness of the program, its safe execution, and successful termination at the moment the new program is being injected to the pipeline. However, OCO can only read from packets. It cannot write to packets, cannot perform some packet modifications. And as we would like to do much more with vSwitch and P4, we decided to change a little bit the design of OCO. So what we did is we moved from programmable filters to programmable actions. And first what we did was to modify the BPF verifier to allow for packet modifications. And we also implemented a new open vSwitch action that allows us to execute an arbitrary BPF programs. In the result, we have a new functionality that is well isolated from the rest of the forwarding pipeline. A flow caching mechanism is also not affected. And in general, impact on the packet processing pipeline is really minimal. And having such an extensibility mechanism integrated, we built the P4 layer on top of that. And the main part of the P4 layer is a P4-uBPF compiler, which allows users to write the data plane extensions for Open vSwitch and inject them in the P4 language and inject them at runtime. So now I would like to talk a little bit about the design and implementation of the compiler, and then we will come back to the Open vSwitch and I will show you how to use our modifications. The main goal of the compiler is to generate the BPF bytecode, which will be compatible with a user space BPF virtual machine. And we inherit from the eBPF backend for P4 compiler, and our solution is also quite similar to P4C XDP compiler. So some concept that I will show you may be similar. Maybe you may be aware of that concept already. As both these solutions, we implement one intermediate stage, which is translating a P4 programs to the C code before they will be compiled to the BPF bytecode by the CLang compiler. A quick word on the differences between user space BPF and eBPF, which is much more popular. So the main difference is the location where the BPF bytecode is executed. And as we use the DBTK data path, we decided to use a user space BPF implementation, which is licensed under Apache 2, so open source license is also different. And uBPF implements more thin virtual machine, so the functionality is quite limited, but it was fine for our use cases. Nevertheless, it provides the support for BPF maps, which provides the key value stores that allows us to share state across incoming packets. And our compiler makes heavy use of these concepts of the BPF maps to implement P4 tables and registers. First, what we did was to design an architecture model for our compiler, and it's really tailored to Open vSwitch. It's composed of the parser and control block, which is composed of set of match action tables, and the deparser. And as I said, the BPF program is a part of Open vSwitch packet processing pipeline. So we decided to disable packet forwarding from within the P4 program. And this is still the responsibility of Open vSwitch to determine an output port for incoming packets. And the only decision the BPF program or P4 program can make is to decide whether to drop the packet or send it back to the Open vSwitch pipeline. And the unique value of our compiler that we see is the support for P4 registers, because it allows users to write stateful network applications for Open vSwitch. Structure of a basic uBPF program compatible with Open vSwitch looks as follows. It is composed of one function called entry, and it takes two arguments. The first argument is a pointer to the context, which in fact is a pointer to the DP packet structure, which represents the packet inside the user space data path. We implemented also a uBPF packet data helper to retrieve packet data from the DP packet structure. And finally, such a function needs to return the decision whether to drop or send the packet back to the Open vSwitch pipeline. And in particular, such a program can process the packet. And in our case, packet processing logic is generated by the P4 compiler. So I will quickly show you how to program a simple P4 program for the Open vSwitch. We need to start from defining the packet headers. In C, the compiler generates a set of C structures. Each C structure has an additional eBPF valid field, which stores the validity bit, which will be used during the deparsing stage to perform an arbitrary packet encapsulation and decapsulation. Next, we need to define the parser to demultiplex the incoming packets. And compiler generates the header structure that will store all the information about the packet headers. And it also generates the set of blocks and go-to statements that maps the logic of the parser. And in particular, we use a set of load functions to copy data from the packet to the local memory, which it means the header structure. Next, we can use the parse headers in the match action tables. In P4, we need to define the key and a list of possible actions for the P4 table. And in C, it's translated. The key that is translated to a specific C structure that stores a key data. And this key data is further used to look up the BPF map, which implements the P4 table. And if a matching entry in the BPF map is found, a switch case statement is used to find an appropriate action for the incoming packets. As I said, we think that the unique value of our compiler is a support for P4 registers. In P4, in order to use the register, we need to just define an additional object called a register, and then we can use read and write operations to manipulate the content of the P4 registers from within the P4 program. In C, the compiler generates an additional BPF map, which implements the P4 register, and we use uBPF map lookup helper to implement a read operation, and we use uBPF map update helper to implement a write operation. Finally, in the P4 program, we need to define the deparser, which is responsible for constructing the outgoing packet before it will be sent back to the packet processing pipeline of vSwitch. And compiler generates a set of blocks that are responsible for filling a packet buffer with data from a header structure. And before the packet will be filled, we need to, and the C program needs to check the validity of if the header is still valid or not, because the deparser needs to handle an arbitrary packet encapsulation or decapsulation. And in P4, we can encapsulate the packet by validating the header, like for example, the MPLS header here. And we can decapsulate the packet by invalidating the header. In C, we use an additional uBPF adjust head helper to change the size of the packet before filling the data of the packet. And we need before we need to define to calculate the offset. If the offset is negative, the bytes are removed from the front of the packet. Otherwise, the 0 bytes are added to the head of the packet. So now I would like to show you how the programming workflow for vSwitch looks like. And let's assume we have a simple P4 program called nat.p4, and it implements source nat. So it has an action rewrite IPv4 that is responsible for rewriting a source IP address of incoming packets. And using first, what we need to do is to use our compiler to translate this P4 program to the C code, and then we can use clang to generate the BPF bytecode that will be compatible with vSwitch. And these two steps are made outside of vSwitch environment, and all these subsequent steps will be a part of the vSwitch environment. We'll use a native vSwitch commands. So if we would like to use the BPF program in our pipeline, we need to load it first to the BPF subsystem by using a load BPF proc command. And we need to pass the BPF bytecode that we just compiled. And we also need to set the identifier of the program. Then we can use this BPF program as a simple vSwitch action just by using the keyword proc and passing the program identifier. And in the result, all the packets that that matches this flow rule will be handled by the dedicated BPF program. We have also implemented the method the command to add a new entry or update an existing entry to the BPF map. And this takes several arguments. except for program identifier, it takes a map identifier, which corresponds to the name of the P4 table. It takes also a key data, which corresponds to the key of the P4 table from the P4 program. And we also have a value data, which is composed of two parts. The first part identifies the action that should be invoked for the packet. And here we have a rewrite IPv4 action that has an index equal to 1. And the second part of the value data, the last 4 bytes, is an action data that will be passed as an argument to the rewrite IPv4 action defined in the P4 program. We have also a command to get the content of the map, to delete a particular entry from the map. And if we don't want to use the BPF program anymore, we can simply unload it from the BPF subsystem. And all these commands are also implemented as OpenFlow messages, so we can control the BPF maps and BPF program from external SDN controller. And we believe that having such a functionality, we can implement a bunch of new use cases for Open vSwitch. And to list few of them, the first group of potential use cases that we see are domain-specific network protocols that are not supported by Open vSwitch yet. And for instance, we have implemented the support for the GTP tunneling in just 200 lines of the P4 code. And similarly, we can implement, for example, a PPOE or in-band network telemetry or any other encapsulation and domain-specific protocol. Another group of use cases are stateful data plane programs, and we can list, for example, stateful firewall or in-network DDoS mitigation. And we believe that we can implement really many other exciting use cases for Open vSwitch. And we also count on the community to use our extensions and bring their own use cases. To summarize, we propose a BPF extension to Open vSwitch that allows us to implement programmable actions and inject particular and arbitrary data plane programs to the packet processing pipeline of Open vSwitch at runtime. And in result, we have a hybrid approach because we keep well-known features and backward compatibility of Open vSwitch, but we provide the support for programmable actions, and we also allow users to write those data plane programs in the high-level P4 language. And as I said, we believe that we can implement many new use cases for Open vSwitch. We hope to merge our backend with the main branch of the P4 compiler soon. And we have still some work in progress. We work on the enhancements to the BPF verifier. We didn't implement checksum computation yet, and we still also work on some performance optimizations. Nevertheless, we plan to open source the modifications to Open vSwitch, and of course, if the Open vSwitch community is interested, we will be happy to contribute it to the main branch of Open vSwitch. Also, I didn't show a demo during this presentation, but if you are interested, please come to me. We can sit together and I will make a quick demo for you afterwards. That's it. Thank you.
Questions?
Hi, thanks. It's a nice presentation. I just want to ask, does it support for the both kernel and the data path? Sorry? It's only user space side. Okay, second thing is, so in the user space now, we have some, if we want to support like some like port mirroring or this kind of scenarios, like or even more complicated scenario like NAT, or is it possible to, or have you done any prototype or this kind of thing or no?
I didn't hear the first use case. You sent contract. For mirror, okay. So no, port mirroring is not possible because, as you saw, it's only an action that cannot make cloning. The cloning is a feature of Open vSwitch, or mirroring is a feature of Open vSwitch. But according to the second part, this not is possible in our opinion. We made some prototyping, and using registers, we can store the state of the incoming, of the session in the P4 program. So it should be possible. I didn't want to touch this topic during this presentation because it will be a subject of my research paper. But our first preliminary results are quite promising. So the performance is comparable to the Open vSwitch without this extension.
Really interesting talk. Couple of questions on BPF action. Do you allow mix and match of BPF action with other actions? And if yes, is there any ordering requirements there? So you're adding BPF as an OVS action. So do you allow mixing of that with other OVS action? That's the question. First question. Second one is, if you do, what are the ordering requirements for the actions then?
So the first question, yes, we do support. We can combine the actions with another Open vSwitch actions. It's totally possible. The only limitation that we have that we need to invoke the BPF action as a last action in the pipeline, because it can modify or encapsulate the packets, and and we do not support recirculation yet. So if subsequent flow rules are, depends on some packet headers that will be changed by our BPF program, it will be tough.
Sorry, originally I also had a question regarding performance, but I was also curious. You mentioned that this platform is also runtime reconfigurable. I don't know if you comment, or at least in the white paper, about showcasing this feature at all. As opposed to you mentioned PISCES, which requires downtime. So I was curious to be able to comment on that at all. So you refer to PISCES, right? Which has downtime, right? Because you need to retarget the source. Would you be able to comment that with your solution, if you guys explored the runtime reconfigurable aspects of it?
If I understood correctly, you asked about if we have an outage of infrastructure, if we update, if we inject the new program to the Open vSwitch, or? Yeah. So okay. So as I said, the PISCES requires the recompilation every time the P4 program is changed. So we need to develop a new P4 program, recompile the Open vSwitch, and then we need to stop and start infrastructure if we want to make a change in the protocol stack. And in our solution, you don't need to do any recompilation. You just load a new BPF program and use it as normal BPF actions, thanks to the BPF virtual machine that we have already integrated with Open vSwitch. So that's the difference.
Let's thank our speaker one more time.